In the last video, we looked at different forms of vectors, right? We looked at the component forms, we looked at writing vectors using unit vectors, and we looked at writing vectors using a magnitude and direction. And I said in that last video that in this video, we'd be able to look at how to go back and forth between them. So let's do that, okay? Let's say that we're given a magnitude and a direction. So let's call it 56 kilometers north, 60 degrees east. And oftentimes this direction here will be written in a little square bracket like such. Now, how do I change this into components? Well, for one, we want to understand what's going on here. So I'm going to make a little sketch, and I'm going to start by writing my cardinal directions here, my north, south, east, and west. Now, 56 kilometers north, 60 degrees east. North 60 degrees east means that if you're looking north and then you rotate your point of view 60 degrees towards the east, that is where your vector would be. So let me write this just a little bit neatly here. This is our vector. It has a 56 kilometer magnitude, and this little angle in here is our 60 degrees, just like that. Now, if you pay close attention here, if you draw a vertical line down from that top of the vector downward, what you get here is a right angle triangle. And I'm going to draw this right angle triangle over here just so we have more space to work. Okay, so it looks something like this. This hypotenuse has a length of 56, right? It's the 56 kilometers. It's the magnitude of the vector. And this little angle in here is 30 degrees. Now, why is this 30 degrees? Because this angle here is 60, so this angle here must be 30 because together they add up to 90 degrees, right? So hopefully that's clear. So with all this information, what we should be able to do is figure out what our x component is and our y component, right? We should be able to figure out these two lengths using the primary trig ratios, SOHCAHTOA, right? Think back to grade 10 trigonometry. If I wanted to figure out this side here, this is your adjacent side, right? You can use cos. Cos of any angle, we'll use the reference angle here of 30 degrees, will equal your adjacent side over your hypotenuse. In this case, the hypotenuse is a value of 56. So I'll put 56 right there. You can solve for the adjacent side. 56 times cos of 30 degrees is equal to the adjacent side. Therefore, the adjacent side has a length of 48.5 kilometers. Okay, so I can even label that over here, 48.5. Now, what about the y direction? That's your opposite side, right? Remember, sine of your reference angle, 30 degrees, will equal the opposite side over the hypotenuse of 56. Multiply the 56 up here, calculate that. I'm not going to show all the steps like I did here, but for your opposite side, you should get as an answer 28 kilometers. So I'll put a 28 right there. So now we know what our x and y coordinates are. So if I wanted to write this vector, and this is a vector, as a vector in component form, all you'd have to say is 48.5, 28, and I would even go so far as to include the units on the outside of this because it is in kilometers. So this vector and this vector are the same thing. Now, you can use a little shortcut here. You don't have to write out your trig ratio every time. What's nice about this is if you have a vector here and you want to find the x component, all you have to do is take that vector magnitude, the 56, and multiply it by cos of the angle that you have here. If you want to find the y component, you just have to take that 56, right, and multiply it by sine of the angle. You can skip right to that step every time. There's no reason to start with this trig ratio. You don't have to do that unless you really want to. You can simply multiply the magnitude by cos of the angle or sine of the angle in order to get these components. So for example, and I'll show you how to do this quickly, if you have a vector like this and you figure out that the angle it makes here is 40 degrees and it has a magnitude of 10, we don't know the units, it's just 10, the x component here is 10 cos 40, and the y component is 10 sine 40. And those are very quick to calculate. You can do so on your calculator, right? The x component is 7.66, and the y component is 6.43, approximately. I'm rounding these to 2 decimal places. So you can simply say your vector is 7.66, 6.43. Nice and easy, right? Now that's how you go from the magnitude and direction to a component vector, right? And you also have the option to write this with the unit vectors, right? You could write 7.66i plus 6.43j. I think it's pretty clear how we go back and forth between these two at this point, right? You shouldn't have any trouble doing that. Now, if I want to go in the opposite direction, if I'm given a component vector, let's say it's 4, 9, and I want to change this so that it has a magnitude and a direction, what can I do? Well, let's start off by writing out or sketching out what this vector might look like. Well, it goes 4 to the right, and it goes up by 9. So that means it starts down here and it goes up to here, just like that. That is the vector we're dealing with. First, what is the magnitude of that vector? Well, the magnitude of the vector, and this vector doesn't have a name. Let's give it a name. Let's call it vector v. Okay, this is vector v. Vector v, if we want the magnitude of vector v, it is going to equal the square root of 4 squared plus 9 squared, right? This is just your Pythagorean theorem that we're doing here, right, to figure out the length of that hypotenuse. And if you do that, you get an answer of approximately 9.85. Again, rounding to 2 decimal places. So that's your magnitude. Now the question is, what is this angle in here? I'll call it angle theta until we solve for it. Well, you can use your trig ratios to figure this out. You have the opposite side, you have the adjacent side, so why not use tan, right? We can say tan of the angle theta is equal to opposite over adjacent. Therefore, theta will equal tan inverse of 9 over 4. And if you do this, you should get as an answer 66.04 degrees approximately. So how do I write my final answer? Well, we can say that the vector v is equal to 9.85. We don't know what the units are, so we can just say 9.85. And then we have this angle, the 66.04 degrees. We also don't know what our directions are. We don't know if this is like a bird's eye view, so we can't be using north, south, east, west. We can't do anything like that. But what we can say is something like this. We can say right 66.04 degrees up. So you can use right to show that you're going to the right, and you can use up to show that you're going up. You can do something as simple as that, and I think that that would be a valid solution, right? There's nothing wrong with this. You could also say that it's 9.85 at 66.04 degrees from the horizontal. You could also state something like that, right? In most questions, you're given a little bit more context and information about the scenario you're dealing with. And when that happens, you're often given some units, right? Some context around your position. And there are things that you can plug in. Like you could plug in your units. You could plug in maybe north and east or whatever it is that you're dealing with depending on your direction. So usually you're given more information. But if not, you can simply do something like this. Now, let's do an example where we have multiple vectors that are magnitude and direction, and we have to add them together. So let's say that you're given this example where we'll say that you're on a boat. I'm not going to write out the whole example, but let's say you're on a boat and you start off by sailing 20 kilometers. I'll say south 40 degrees west. South 40 degrees west. That's the direction you're sailing in. And then you turn, right? You make a turn, and all of a sudden, you start sailing for 30 kilometers, and you're in the direction north 10 degrees west. The question will be, what is your displacement? Where are you relative to where you began? That is the question. So, let's maybe make a little sketch here. I'll use my cardinal directions, north, east, south, west. You start off by sailing south 40 degrees west. That means something like this, where this is 40 degrees, right? This has a magnitude of 20 kilometers. So south, and then you turn 40 degrees towards the west. That's what this means. Okay, and then where you end up here, you have to make a new set of cardinal directions because you're given this, right? So now we're going to be traveling north 10 degrees west. So it's going to look like this, where this angle in here is 10 degrees, right? It's 10 degrees between this new vector and the north direction. That's 10 degrees. The question is, where do you end up relative to where you started, right? And remember, this is 30 kilometers, this magnitude. So what is this vector here going to look like? Where are you going to end up relative to where you started, right? Well, there's a lot of work that we can do here, and you can figure this out one of many ways. You can use different trigonometric principles. You could use cosine law, for example, to help you get started, sine law, all that type of stuff. Or you can break these down into their components. And if you decide to break them down into their components, that's a really nice way to start working once we start dealing with vectors, because that method will work no matter how many vectors you have. In this case, you only have 2 vectors. But if you had like 5 vectors, well, what you end up with isn't going to be a nice triangle like this, right? And so you want to get used to using those x and y components to solve questions rather than relying on, sine law, cosine law, SOHCAHTOA, that type of stuff. Because again, you're not always going to have one nice triangle. So let's break these things down into their components, and let's start with the x direction. So let's discuss the displacement in the x direction. What do we have? And for the sake of just making sure everything's consistent and makes sense, I'm going to say that our values as they go to the right are positive. Okay, so we're working in the x direction here. We're assuming that values to the right are positive and to the left are going to be negative. Okay, so what is the x component of this? Well, this vector is this triangle here, right? It's that magnitude of 20. How do we figure out the x component of that? Well, it's going to be 20 times sine of 40 degrees. Well, hang on. In the last example, I said we use cos to find the x direction. Yeah, but we're talking about this vector here, the vector that goes down like this, right? The angle we're given is at the top. It's this 40 degrees. If I want this x component, I have to use sine because sine is opposite of that 40 degrees, right? So that's why I'm using this. Now, don't forget, we said that as we go to the right, we're going to have positive values and to the left will be negative. Well, this is going to the left, so I should make sure to put negative 20 right there. Now, what about this one? Well, we're going to have another negative because this is also going to the left, so I'm going to have negative 30 multiplied by, is it sine or cos? Well, this triangle looks something like this, where this is 10. I'm interested in finding the x direction that's opposite to where my angle is. So again, I'm actually going to be using sine of 10 degrees. So I don't want to say that's unusual, but a lot of the time we're used to that reference angle being here or here. And so most of the time our x direction, our x component, is found by using cos. In this case, though, we're not using cosine, we're using sine. And it happens to be that way just because of where our angles are located, right? So no problem doing that, right? That's absolutely okay. You can solve this and figure out what you get. If you do so, you should get negative 18.07 approximately. Now remember, this is in kilometers. So we can say 18.07 kilometers. And notice I got rid of that negative. That's because the negative just indicates the direction. And so because we're going to the left, that's what that negative means. We can simply say that it's 18.07 kilometers west. Why am I using west? Because to the left in this situation is west, right? Because this is a bird's eye view. If we were going to the right, we would use east. Because we're going to the left, we will use west. Hopefully that makes sense. Now that was for our x direction. We will now do our y direction, so the displacement in the y direction. And I'm going to say that up is positive, or in other words, north is positive, okay? Now let's figure out the y components of each of those vectors. It's going to be the same as these, except instead of sine, we're going to use the opposite. We're going to use cosine. But keep in mind our signs, right? these were negative because they were both going to the left. In this case, we said up is positive, down is negative. Well, are we going up or down in these cases? Well, in this case, we're going up. In this case, we're going down, right? So this has to be positive. So when we take this term, it's going to be positive 30 cos of 10 degrees. But this is going downward, so it's still going to be negative 10 cos 40 degrees. Okay, so just to recap, this is negative because we are going downward, we are going south. This is positive because we are going up, right? And we said up is going to be positive. So we get those answers. It's very important that we get those signs correct. And the answer we get is 14.22, or you could say 14.22 kilometers north. Okay. If you messed up those signs, if you said they were both negative or both positive, then instead of working against one another, they would work together and you get a much larger number here. I think 50 something kilometers. That's not what you want. You want to make sure that one's positive, one's negative, because again, if you look at that original sketch, one of them is going downward, one of them is going upward, right? And the result is a small increase towards the north from where we started from, right? It goes up a little bit. So we want to keep that in mind. Now, what do we get for our final answer? Because we need to provide a final answer. We've got two answers here. We've got 18 kilometers west and 14 kilometers north. You could represent that in a component form, right? You could say 18, or I should say a negative 18.07 because it's to the left, right? That's what west is. And then 14.22 kilometers north, and then say this is in kilometers. You could provide that as an answer, but we were given the original vectors in magnitude and direction form, so we should provide our final answer as a magnitude and direction as well. So let's think about this. If we go 18.07 kilometers west, and then 14.22 kilometers north, what is the resulting vector? Right? These are the x and y components of our answer. So what is this vector? Well, we can figure out what its magnitude is using the Pythagorean theorem, right? If I call this vector v, then I can say the magnitude of vector v is going to equal the square root of 14.22 squared plus 18.07 squared. And if I do that math, then I get 22.99 kilometers, or I'll just say 23 kilometers. And now we have to figure out what angle, right, what direction we're going to assign to this, because a magnitude alone is not good enough for a vector. We also need our direction. Well, we can figure out what this angle in here is. I'll call it angle theta for now. I'll say tan of theta is equal to, we'll use our opposite over our adjacent, right? So 14.22 divided by 18.07. Take the tan inverse of this to get theta, and if you do so, you should get 38.2 degrees. Now, 38.2 degrees, we can't just leave it as an angle. It needs to be an angle relative to something, right? Well, if we're starting here and we're ending here, we can think of our cardinal directions from the starting point like this, right? North, east, south, west. If this angle in here, theta, is our 38 degrees, usually we want to state north first or south first when we come up with those combinations for directions. You'll notice that up here in the beginning, we always have south and then west, north and then west. We never want to start with west or east. You always want to start with south or north instead. That's kind of the standard way to do it. And so I'd like to, for my answer, write north something west. So really I want to have this angle in here instead. So instead of 38.2 degrees, what I'll use is 90 minus 38.2. And if you do that, what you should get is 51.8 degrees. So for my direction, I'm going to say north 51.8 degrees west. That's going to be my direction. So for my final answer, vector v is equal to 23 kilometers north 51.8 degrees west. That will be my final answer. And we can see if it makes sense. We can look at our initial sketch that we made up here. Does it look like this line is going northwest. Yeah, it does. And remember, it's a very crude sketch, right? It's more like this than it is like this, right? So we're off a little bit with our sketch. It's definitely not to scale, but that's okay, right? It's in the general direction that we expected, so I would be pretty confident in our final answer.